Welcome to Technically You, the show that makes the strange world of quantum tech just a little more familiar. Today, we're diving into something that's shaking up cybersecurity like an earthquake, Shor's algorithm.
That's right. It's the quantum juggernaut with a knack for breaking encryption. And we're not exaggerating. If classical cryptography is a fortress, Shor's algorithm is the battering ram that quantum computing might use to break in. So what is Shor's algorithm?
Shor's algorithm, developed by Peter Shor in 1994, is a quantum algorithm specifically designed to factor large integers. And if that sounds boring, trust us, it's a massive deal in the world of cryptography.
Exactly. Most of the encryption we rely on today, RSA for example, based its security on how difficult it is to factor really large numbers. Classical computers would take millennia to do it. Quantum computers using Shor's algorithm, a few hours, maybe minutes. Let's talk about how it works.
At its core, Shor's algorithm relies on the principle of period finding, identifying repeating patterns in mathematical functions. But it does this using a quantum trick called quantum parallelism.
And here's where quantum magic happens. Shor's uses a quantum Fourier transform to find the periodicity of a function. That's a fancy way of saying it uses quantum waves to spot repeating patterns incredibly fast.
Once the period is found, you can use some basic math to reveal the factors of a number. And just like that, encryption goes poof.
Since quantum Fourier transform is a new term for most of us, here is a short definition of QFT. A QFT is a quantum analog of the classical discrete Fourier transform. It operates on the amplitudes of a quantum state, mapping them from the computational basis to the frequency domain. Specifically, the QFT transforms a quantum state into a superposition where each component corresponds to a distinct frequency. This transformation is a fundamental building block in many quantum algorithms because it efficiently reveals periodic patterns hidden in quantum states. QFT is most prominently used in Shor's algorithm for factoring integers and solving the discrete logarithm problem.
Wow, that was a mouthful. That definition wasn't easy to simplify. While we are at it, let's touch on what encryption does QFT break.
Shor's algorithm specifically threatens public key encryption schemes like RSA, DSA, and ECC. Basically, all the stuff that secures your online banking, emails, VPNs, and even government secrets.
RSA relies on factoring large prime numbers. ECC, or elliptic curve cryptography, relies on the difficulty of solving discrete logarithms on elliptic curves. Shor's algorithm busts both of those wide open.
Now, don't panic just yet. Quantum computers that can run Shor's algorithm at a useful scale, meaning hundreds of logical qubits with low error rates, aren't quite here.
Yeah, most current quantum machines top out at a few hundred noisy qubits. To break RSA 2048, we'd need several thousand logical qubits, which means millions of physical qubits, considering error correction.
There have been experiments, though. In 2001, IBM used a 7-qubit quantum computer to factor 15 into 3 and 5. Baby steps, but it's symbolic of where things are headed.
And more recently, there have been lab-scale demos factoring small integers. It's proof of concept stuff. But the writing is on the wall for current cryptography.
That's why we're seeing such a push toward post-quantum cryptography algorithms designed to withstand attacks from quantum computers.
NIST is currently finalizing standards for quantum-safe encryption. These new cryptographic methods rely on problems that even quantum computers can't easily solve, like lattice-based cryptography. We cover post-quantum cryptography in another podcast.
If you are wondering if we need to worry, I'll say yes, it's not about waiting for a quantum computer that breaks encryption tomorrow. The real threat is harvest now, decrypt later. That's when attackers collect encrypted data today and decrypt it in the future with a quantum machine.
Exactly. If your business is storing sensitive data that needs to stay secret for 10 plus years, think healthcare, defense, or finance, you need to start thinking quantum resistant now. So What is the future of quantum algorithms?
Shor's algorithm is just the beginning. As quantum computers become more stable and powerful, we'll likely see even more groundbreaking algorithms emerge.
That means now's the time to invest in research, training, and infrastructure that can adapt. Whether you're a software engineer or a CISO, quantum readiness is your next frontier.
And that's it for today's podcast on Shor's algorithm. If you like this episode, be sure to subscribe and share, because quantum is no longer science fiction, it's just around the corner.
And remember, encryption is only as strong as the math behind it. In quantum math, it's coming to shake things up. And as always, stay curious.